Hello everyone, welcome back to our course on mechanical behavior of materials part 2. So in the last lecture, we discussed about uh, the calculation from Westergaard and approximate solution given by Irwin's on the stress distribution ahead of the crack tip, right? So we'll discuss about this a little bit more. Then we'll come to the stress triaxiality at the crack tip. uh, we'll discuss about that as well today. So what we found was that overall there was a use of complex numbers and airy stress functions okay. So Westergaard used these complex numbers and airy stress functions and came out with the exact solution of stress field ahead of the crack tip. That is what we discussed. So you get Westergaard's complete solutions for stress field near crack tip. Okay. Then we discussed about the Irving approximate solutions. So Irving's approximate solutions for the stress field near crack tip. And if you remember, when we discussed about Irving solution, we introduced the concept of K, which is stress intensity factor. Okay. Again, I am reiterating, please understand the difference between stress intensity factor and stress concentration factor that was discussed in the last class. Okay. So now let's compare the Westergaard complete solution and Irwin's approximate solution and try to understand why Irwin's approximate solutions are very useful in the fracture mechanics. So comparison of Westergaard's solutions with Irwin solutions. Okay. And we will calculate that at the crack plane. Right? That means y equal to 0 and theta equal to 0. So theta equal to 0 is for Irwin and y equal to 0 for Westergaard. We discussed that, right? So what was the Westergaard solution? At the crack plane, and we will focus on sigma yy. So if you have a crack here, so x is in this direction and y is in this direction. Okay. And if you remember, r was this and theta was this. Right? So Westergaard solution was sigma yy equal to sigma infinity divided by root over 1 minus a by s whole square. And then Irwin solution, that is sigma yy equal to sigma infinity root over pi divided by root over 2 pi r. Okay, so all theta term, if you remember the Irwin solution, there was f theta term that will be 0 because theta here is equal to 0. So you are going to get sigma yy as this particular expression. Okay. Also along the crack plane, if you remember, we had discussed that x equal to a plus r, right? So let me draw a complete crack, something like this. And Westergaard origin was this point, right? So any point ahead of the crack tip will be given by a plus r cos theta, right? But theta is here is 0, so cos theta becomes 1. So overall x will be given as a plus r ahead of the crack tip. Okay. Now let's put some values of x and compare the solution by Westergaard and Irwin. Okay. So I'm putting some values now. So we'll calculate sigma yy by sigma infinity. Okay. So x, and then we have Westergaard and then Irwin. Okay. So if S is equal to A, so you have one equation, number 2 and number 3. Okay. So if we know the value of X, we can calculate the value of R from equation 1. And then we can use the value of R in equation number 3 to figure out what is sigma yy by sigma infinity or vice versa. Okay. So the Westergaard solution from equation 2, if S is equal to A, this will tend to infinity. Okay. And Irwin solution, so S is equal to A, so R will be 0. So your value tend to infinity. And we are calculating, remember, the value of sigma yy by sigma infinity. So this is the value we are calculating in the table. Right? Now if I put 1.5a, so x is equal to 1.5a. Okay, so if the Westergaard equation will be 1 by root over 1 minus 1 by 2.25. Okay, so just put the value of x as 1.5a. So it will be 1 minus 1 by 1.5 square. This will come out to be something like this, and it is equal to 1.34. Okay. Now it's S is equal to 1.5a, R will be 0.5. Okay, A. So your sigma infinity, sigma y by sigma infinity, that will become equal to root over pi a divided by root over 2 pi into 0.5 a. So if we calculate, this will be 1. Okay. So see, if R equal to 0.5a, you are going to get sigma yy equal to sigma infinity. That means the stress ahead of the crack tip along y direction will be equivalent to the far field stress. Okay. But Westergaard is predicting as it is higher than 1. Okay. Now let's come to 2a. So we can calculate that like this. Okay. So this will be 1 minus 1 by 1 by 4 and 1.154. Similarly, R will be A, and sigma yy by sigma infinity, that will be root over pi a by root over 2 pi a, and will be 1 by root 2. Then if I put 3a, this is going to be 1 minus 1 by 9. So 1.06. And if I put R equal x equal to 3a, R is going to be 2a. So this value will be divided by 4 pi a, so half. Similarly, 4a, then 1 minus 1 by 16, and this is going to be 1.03. R is going to be 3a, and this value is going to be pi a by 6 pi a, so 1 by 6. Now, if I continue to do that, and then let's come to our far field. Okay, so very far away from the track tip. So let's say x tends to infinity. Okay, so sigma yy will become equal to sigma infinity. If you see equation number 2, right? So this will tend to 1.0. And if r tends to infinity, sorry, s tends to infinity, r will also tend to infinity, right? And if that is the case, sigma yy by sigma infinite becomes equal to 0. This value tends to 0. Okay. So now compare the values given by Westergaard and Irwin. So at the crack tip, where x is equal to a and r equal to 0, you are going to get infinite stress. Both are okay. If you go on increasing the value of x and correspondingly a, you are going to see a decreasing values in both the cases. But remember, the decrease in the Irwin solution, right? Or decrease in the stress provided by Irwin is much, much higher than the Westergaard. Okay, that is observation number 1. And the second observation is, we know that, there is a stress concentration ahead of the crack tip. We have discussed this. So ahead of the crack tip, we are going to get higher stress. And, as you go away from the crack tip, it is going to be similar to sigma infinite, which is far field stress. And that is what Westergaard is predicting. So if you see at the crack tip, Westergaard is predicting that it is going to be infinite. Okay. Far away from the crack tip, it is going to be equal to the far field stress. So sigma yy is equivalent to far field stress. So physically, it is correct, right? Irwin solution at the crack tip, it is predicting it to be very nicely that it is going to be infinite, same as what Westergaard is predicting. But away from the crack tip, it is predicting it to be 0. That is not physically correct, right? However, if you see r equal to 0.58, it is predicting the same as what Westergaard is predicting far away from the crack tip. That is, sigma yy is going to be sigma infinity. So the second observation is that very near to the crack tip, Irwin solution is predicting the similar behavior as Westergaard, and we can safely apply Irwin solutions of stress ahead of the crack tip near to the very near to the crack tip, but not far away from the crack tip. That is observation number 2. Okay. So from this table, we can make these 2 observations. So let me plot now for better understanding. So this is your crack here. Okay. So I am plotting sigma yy by sigma infinity, which we calculated. Okay. So one is here. That means sigma yy is equivalent to sigma infinity. Okay. And this line, what I am drawing now, is your crack plane. So this is crack plane. So let me put a value of x here. Okay. So what is the value at the crack tip? S is going to be a, right? The half crack length, and r is equal to 0. Then we can put say 2a, then 3a, then 4a, and so on. Okay, it can continue like that. So if you see the table for Westergaard at the crack tip, it is equal to, or it tends to infinity, right? So this is your Westergaard solution, tends to, let me put 1.5 A here also somewhere. This is like 1.5 A. So your Westergaard solution is going to be say something like this. Okay, not up to the scale. You can actually place the value of sigma y by sigma infinity depending upon A up to the scale as I have shown in the table. But what needs to be seen here, that as S tends to A, Westergaard is predicting the solution to be infinite, and as H tends to infinite far away from the predicate, the stress sigma yy is going to be equal to sigma infinity, and that is what we are seeing here. Okay. Now, if I plot the solution for Irving, so at 1.5a it is going to be 1, we know that, and far away from it, it is going to decrease and finally tending to 0, right? So we can predict something like this for Irving. Okay. Something like this. Okay, again, not up to the scale. You know the value of x, you can figure out a r, and then from the table, what we discussed, you can plot the exact value of y and get the third. Okay, so here the red one is Westergaard solution, and the blue one is Irving solution. Okay, and whatever we discussed can be nicely seen here, both the plots. Okay, so here, very near to the track tip, right? You see that the Westergaard solution is matching with the Irving's approximate solution. Okay, so we can nicely use Irving approximate solution in the fracture mechanics at very near to the practice, right? Remember, the advantage of using inverse solution, I have mentioned that it is based on R and theta and K. So at a given point, you know R and theta. So if you can calculate somehow the value of a stress intensity factor, you can very easily calculate the stress at that particular point, right? That is the advantage of Irwin. But again, that was approximate solution. So we can, based on the plot in the table I have just discussed, we can use the approximate solution very near to the crack tip. We cannot use it safely away from the crack tip, as you can see in this plot. Okay. So note Irwin's approximate solutions are very well valid near to the crack tip. Okay. And remember that this is what is important. You want to understand the stress distribution near the crack tip, because the crack growth is going to in turn depend upon the values of, or in the nature of the stresses near the crack tip, not far away from the crack tip. Okay. Okay. So we have discussed Irwin's and Westergaard. Let me point out one more important thing, that if you remember, we discussed about mode 1, mode 2, and mode 3, and depending upon which mode is applicable, the stress intensity factor can be given as K1, K2, and K3. Okay, where 1, 2, and 3 here are mode 1, mode 2, and mode 3. Okay, we are going to talk about K1C. I have seen many students saying KIC. No, it's K1C. That means we are talking about mode 1 loading, and then we are calculating the fracture toughness. We'll discuss about that eventually. But remember, it's K1C, it's not KIC. Okay, that is one. And second, we also discussed that at theta equal to 0, you are not going to have any shear stresses. That means at the crack plane, whatever stresses you have, those are principal stresses because there is no shear stress. Okay. So theta equal to 0. So if you remember, the solution for Irwin was r theta equal to k1 by root over 2 pi r f theta. Okay. And at theta equal to 0, f theta terms goes out to be 0. Sorry, f theta term you have to calculate, and you will see that tau xy comes out to be 0, right? So at theta equal to 0, which is crack plane, shear stress tau xy equal to 0. Okay. So in mode 1 loading, at the crack tip, the stresses are principal stresses. Again, in the crack plane. Okay, on the crack plane, not at other points we are talking about. We are talking about only at the crack plane. Okay, we are going to use this when we discuss about the Tresca criteria later. Okay, so this is important. So what is the conclusion now? We can draw sigma yy as, and if this is my crack here, it is going to decrease with respect to distance, right? So it is going to be maximum at the crack tip, and it goes down away from the crack tip, and finally it is going to reach to sigma infinity, that is far field stress. Okay, so this is the nature of stress field distribution sigma yy, where y is in this direction and s is in this direction. Okay, so this is the nature of the stress distribution. It continuously goes down. Now, if you see, you have sigma xx also, sigma yy also, right? That means you can have stress triaxiality, right? If you have sigma zz also, isn't it? We were talking about the plane stress condition. That's why we have sigma yy and sigma xx, right? So, why we are getting the stress triaxiality in the presence of the notch or crack? That question comes into mind now, and that is what we are going to discuss. So stress triaxiality. Okay. So now let's consider a notch. Okay. And we know the stress distribution here is going to be something like this. Okay. Now I'll change the notation. I will make this as one direction. So y here will become 1 1, and then s here will become 2 2 direction. Okay. So this is the nature of stress distribution or stress profile of sigma 1 1, which is sigma y yy. Okay, we have discussed this. So this is direction 1 1, and this is direction 2 2. Okay, or 1 or 2, whatever. So now let's consider small specimen in front of the crack tip. So let me magnify it now. So I'm talking about a notch, okay? And then I'm considering small specimens like this ahead of the crack tip. So they are all joined together. Okay? Just for schematic purpose, I am making it separately. And assume that these all are like tensile samples, micro tensile sample, very small specimen ahead of the crack tip, and so on. We can continue like this. Okay. Now at the crack tip, we know the stress sigma 11 is the highest, and it goes down to sigma infinity as we move away from the crack tip, right? Now think about the tensile testing we have discussed before, right? So if your stress is the higher, right, the contraction along the S direction, right, or along the other direction is going to be also highest, right, because of the Poisson's effect, right? We have discussed that during tensile testing in the first course, the mechanical behavior of materials part 1. Okay. So we are going to apply the same logic here. So let me mark these as 1, 2, 3, 4, 5, 6, and so on. Right. Say now I will give some random number, say 15, 16, some random number, right? Far away from the rectum. Okay. So in the sample specimen 1, you are going to observe the highest tension as well as the highest contraction. Sample 2, it is going to be slightly lower than the sample 1, and so on. And if that is the case, physically you should observe voids between sample 1 and sample 2 and sample 2 and sample 3, because sample 1 has contracted more than the sample 2, right? So there should be a generation of voids, but we do not see that, right? Physically, we do not observe that. That means there is a stress acting along the horizontal direction, which is 2, 2 here, which is not allowing to form those voids. And that is the genesis of having sigma 2, 2 along 2, 2 direction. Although we are applying the only, the say, uniaxial loading, but because of the presence of notch, because of the variation of sigma 1, 1 along the crack plane, you are going to observe different contraction, right? Which could have led to the formation of voids, which we do not see practically. So there is a genesis of sigma 2, 2 along the in the crack plane. Okay. Again, remember the sigma 1, 1 plot, what I have shown here is on the crack plane. So in maximum time during my lecture, I am going to talk only about the crack plane. Okay, so let me write down what we discussed till now. So due to effect of Poisson's ratio, I say Poisson's effect, right? Specimen 1 will try to contract more than specimen 2. Okay, because the stress at 1 is the higher than at 2. Okay. Similarly, 2 will shrink or contract more than 3. Okay. And this will continue. So and so on. Okay. So this should lead to the generation of voids. But physically, we do not observe that. That means there is some stress acting along the horizontal direction, which is not allowing to happen the formation of voids. So this will result in the development of stress along direction 2 2. That means now we are having sigma 2 2, right? We have sigma 1 1, but because of the variation of sigma 1 1 along the thread plane, you are going to have a development of sigma 2 2, right? Now the nature of sigma 2 2 should also follow like sigma 1 1, right? Because it is developing because of the sigma 1 1, right? So if I do that, I have sigma 1 1 like this, okay? Sigma 2 2 should also be say something like this. So this is sigma 1 1 and then this is sigma 2 2. Ideally, it should be like that. But remember, the track surface or north surface here is a free surface. There cannot be any stress along the horizontal direction, right? So the actual nature of the stress along 2 2. So let me draw for sigma 1 1. So sigma 1 1 is going to be something like this. So this is sigma 1 1. Now sigma 2 2. So stress at the notch tip, since this is a free surface, here it is going to be 0, right? But we know the actual nature should be continuously decreasing, right? So overall, sigma 2 2 is going to be something like this. Okay, and not like this. I'm going to just cut it. Okay. So sigma 2 2 is 0 at the notch tip. It goes to maximum at a certain distance ahead of the thread tip and then it decreases continuously. Okay. And sigma 1 1, it continuously decreases ahead of the thread tip. Okay. And this is happening because this is free surface. So sigma 2 2 is equal to 0. Okay. So now you have understood the variation of sigma 2 2 and sigma 1 1 ahead of the practice. Okay. Now let me come to another concept of plane stress and plane stress. So depending upon the stress condition, whether it is plane stress or plane strain, the variation of sigma 3 3, you are going to see that will be completely different. Okay. So first, let me try to explain in very short what is the difference between plane stress and plane strain condition. Okay. So plane stress and plane strain. Okay. So whenever we have very thin plate, right? And now we know this at the surfaces, free surfaces, stresses are going to be 0. So for all practical purpose, since the plate is very thin, we will assume that the stress doesn't change through the thickness. Okay. That means along the thickness direction, you are going to have 0 stress. And that is plane stress condition, right? In plane strain condition, we talk about the thick specimen. Okay. So your thickness along one direction is much higher than the other two direction. So for all practical purpose, the strain along the higher thickness direction, we will assume it to be 0. there will be some strain, right? But for all practical purpose, the strain is so small that we will assume it to be 0. So that is plane strain condition. Okay. So for plane strain, so plane stress is for very thin plate, and plane strain thick plate. Okay. So here we are assuming sigma 33 to be 0. So along the thickness direction. Because it is thin, so throughout the cross section, we will assume it to be 0. And for thick plate, epsilon 33 is equal to 0. So along the thickness direction, or the thicker, the highest dimension one. Okay. So these are the two conditions. Quantitatively, we can say sigma 33 equal to 0 for plane stress and epsilon 33 equal to 0 for plane strain condition. Now let us utilize these two concepts and then assume that the material at the thread tip is also behaving perfectly elastically. Then how the variation of stress will be there in the thread plane ahead of the thread tip. Okay. So now if you remember the theory of elasticity, what was discussed in course 1, if I have a body element, so let's see sigma 11, sigma 22, and then sigma 33. Okay. So three-dimensional body and three-dimensional stresses is all tensile stresses. Okay. So we are assuming the body to be elastic. Okay. So we can write epsilon 11 as 1 by E sigma 11 minus mu sigma 22 plus sigma 33. Okay. Go and look at the videos for mechanical behavior of materials course 1, and you are going to see this equation, right, for epsilon 11. Similarly, we can write for epsilon 22 and epsilon 33 and epsilon 22 and 33, right? And how does it come? Let me quickly prove also. So strain along x1 direction. So this is very simple, right? So due to sigma 11, it is going to be sigma 11 by E, right? So if I assume that only sigma 11 is there, so strain along 11 direction is going to be sigma 11 by E, right? Where E is Young's modulus. Okay? Due to sigma 22 is going to be minus mu sigma 22 by E due to Poisson's effect. Okay? And due to sigma 33 is going to be minus mu sigma 33 by E. So strain along one direction. Okay, let me write down one direction. Okay, so strain along one direction because of sigma 11, sigma 22, and sigma 33 will be given like this. So we have to just superimpose to compute the strain along one direction because of sigma 11, sigma 22, and sigma 33, and that will be epsilon 11 equal to just sum sigma 11 by E minus mu sigma 22 by E minus mu sigma 33 by E. So you don't need to remember, you can actually derive it very nicely, right? And if you do that, you're going to get the equation like this, which is also written at the top. Okay. Similarly, you can have expressions for epsilon 22 and epsilon 33. Okay. So epsilon 22 is 1 by E sigma 22 minus mu sigma 11 plus sigma 33. Okay. And epsilon 33 is 1 by E sigma 33 minus mu sigma 1 1 plus sigma 2 2. Okay. So now we know it's epsilon 1 1, epsilon 2 2, epsilon 3 3. Okay. And we discussed about the plane stress and plane strain condition. Okay. So let's talk about plane strain condition. Epsilon 3 3 is equal to 0. Right? We just discussed. So let me mark here. So let's put this epsilon 3 3 equal to 0 here. Okay. So this particular equation in combination with epsilon 3 3, it is going to be 0 and then complete expression on the right side. Right? And finally, we can write sigma 3 3 equal to mu sigma 1 1 plus sigma 2 2. Okay. So sigma 3 3 is going to be mu into sigma 1 1 plus sigma 2 2. Right? We know the stress distribution ahead of the track tip on the track plane for sigma 1 1 and sigma 2 2. Right? So we can now plot what is going to happen for sigma 3 3 in plane strain condition. Right? So you have a notch here. So this is a track plane. Again, I'm reiterating, we have been talking about only about track plane. So stress goes something like this. Okay. Now sigma 2 2 is like this. Okay. And what is sigma 3 3? Sigma 3 3 is mu sigma 1 1 plus sigma 2 2. So it is going to lie between sigma 1 1 and sigma 2 2. Right? So it will be given something like this. So see at track tip sigma 2 2 is 0 and sigma 3 3 is going to be infinite. Right? So average, if I take not the average, it's mu times sigma 1 1 plus sigma 2 2, it is going to be something like this. In between these two. Okay. So this green one here is sigma 3 3 and the red one is sigma 2 2 and blue one is sigma 1 1. Okay. And the direction is sigma 1 1, sigma 2 2 and then sigma 3 3. Sigma 3 3 here is on the negative side, but just realize that it is along the board, right? Into the board and along the thickness direction. So this is the stress distribution you see when you have plane strain condition. Okay, where the minimum is sigma 2 2, maximum is sigma 1 1 and sigma 3 lies between these two. So what you observe here is that although you have say a uniaxial tension, if there is a presence of notch or track, okay, you can have triaxiality in front of the track tape in plane strain condition. Okay, so in plane strain, presence of triaxiality at the notch, okay, or ahead, right? You can see. And this is happening why? Because you have the presence of notch or crack. Okay, you have triaxiality. Okay, and this is very, very important. You also see this when we were talking about the tensile loading, right? Uniaxial tensile test. So after the presence of neck, after neck forms, it is somewhat a situation like a notch, right? So although you were applying uniaxial loading, due to the presence of neck, you are going to see triaxiality in front of the neck, right? That is what we had also discussed before. And in the case of now plane stress, sigma 33 is 0, right? We have discussed this. So in plane stress, you are going to have biaxiality. Stress distribution. So you have sigma 11 and sigma 22 and sigma 33 is not there. So in the case of plane stress, again, this is plane stress, what we are discussing now. We are going to have only two stresses. So sigma 11 will be there. Okay. And then you are going to have sigma 22. Sigma 33 is 0. So you have biaxiality in plane stress and triaxiality in plane strain because of the presence of notch or crack. Okay. So we assumed here that there is a elasticity, right? Complete elasticity. So in the next lecture, what we are going to talk about is the small scale yielding ahead of the crack tip, and then we will see how this is going to change. The nature of the curve is going to change when we have small scale yielding or local plasticity ahead of the crack tip. Till now, we have assumed it to be completely elastic uh, behavior. Okay. So we'll stop now and we'll meet in the next lecture. Thank you.